Hi, everybody. My name is Angela Jensvold, and today we're going to finish up gravitation by talking about orbits. And then tomorrow we're going to start review. So after today, all of our sessions will be review. Okay, let's take a look at this problem I gave you for homework on Friday. So this is an old AP multiple choice question. So you have the Earth and the Moon not drawn to scale. And the distance between their centers is d, and it's asking for the acceleration of an object, let's just call it object x, that's halfway between them. Okay, so we've got our sketch. So let's do a force diagram. You've got the force of the Earth on object x, and then you've got the force of the moon on object x. I drew it smaller since the distance is the same, but the moon's mass is smaller, so the attractive force will be smaller. Okay, so now let's apply Newton's second law. Sum of forces over mass is acceleration. And in this case, it would be the force of the moon on object x minus the force of the Earth on object x all over the mass of the object that we're summing the forces on, and that's object x. Okay, so then you get force of the moon is g mass of the moon, mass of object x over how far apart are their centers? D over 2 minus g mass of the Earth, mass of x over how far apart are their centers? Also d over 2. And then you divide everything by the mass of object x. Luckily, that's going to cancel. And if you square the denominator, and then whenever you divide by a fraction, you flip it up. So it would be 4g over d squared times mass of the moon minus mass of the Earth. And our answer is just the negative of answer A, and it's looking for magnitude. So if we take the absolute value of our answer, we get A. So I hope you guys got A. Okay, so today we're going to look at we have 4 learning objectives. They're all conservation based. The first is to calculate. We know how to calculate now, hopefully from Friday. You remember how to calculate. We're going to be calculating period, speed, and radius of an orbiting object. We're going to stick to circular orbits. That's according to the learning objectives in the course and exam description. And then the new skill we're going to learn today, which that skill is still tested on this year's AP exam, is Derive. So Derive Kepler's third law for circular orbits. And then we're going to calculate gravitational potential energy of a satellite Earth system and also the kinetic energy. And then we're going to derive, again, practice our new skill of deriving the relationship of total mechanical energy of a satellite Earth system as a function of R. Okay, so those are our goals for today. So what does derive mean? So on Friday, we talked about calculate, which is showing a series of steps with the algebraic equations and substituting your numbers and putting units on your answer. And then we did describe, which is more qualitative. And then derive is probably the highest bar of any prompt you're going to see on the AP exam. Derive means perform a series of mathematical steps using laws. I would add, you basically start from first principles. So you're going to start from something on the equation sheet or a fundamental law like conservation of energy, conservation of momentum, and then you show every single step of your work, including everything you had for calculation. So derive could be more based on variables, but you definitely start from first principles. So, all right, so our first goal is to be able to calculate the speed, the orbital speed of a satellite Earth system. So let's draw a sketch of it. So let's say you had the Earth and some satellite. Whoa. some satellite, and it's in orbit around the Earth, okay? What are we going to do if we don't know how to start? We draw a force diagram. That's what we do. So this satellite has the force of the Earth on the satellite. Remember, a force is an interaction between two objects. The two objects here are the Earth and the satellite, okay? So let's apply Newton's second law because it worked so well for us on Friday. We're going to sum the forces on the satellite. Okay, so the forces on the satellite are G, mass of the satellite, mass of the Earth, divided by the orbital radius squared, all divided by the mass of the satellite. We're dividing by the mass of the satellite because that's the object for which we're summing the forces. Okay, and luckily that is going to cancel. So the mass of the satellite cancels, and you get G mass of the Earth over orbital radius squared. Okay, if you remember from circular motion, if an object is moving in a circle, its acceleration is v squared over r, and this would be the orbital radius. R is the radius of the circle it's moving in, so that would be the orbital radius. So that's equal to G mass of the Earth over orbital radius squared. One of those radii will cancel, so let's do that, and then we'll get our expression for the orbital speed of a satellite around any planetary object. I'm not putting a subscript on the M because sometimes it's not the Earth that's being orbited. It could be the sun, it could be anything. So that M is the mass of the object being orbited. So that's important. And then R is the orbital radius. Okay, you might want to write that down because we're going to use it in a minute. Okay, now our second goal was to derive Kepler's third law. So let's draw the same diagram we had a moment ago. So the satellite is orbiting the Earth. What are we going to do? Force diagram. Force of the Earth on the satellite. Okay, so we're going to apply Newton's second law. So remember, I said derive means starting from first principles. So the first thing we're going to write on our paper is something fundamental. This time, it's going to be something from the equation sheet. It's going to be Newton's second law. But another time, it might be conservation of energy or conservation of momentum. And you could write out in words, momentum is conserved, or you could write P initial equals P final, or delta P is 0. Doesn't matter, as long as you start with something fundamental. Okay, so, I mean, this is sort of the same path we took a moment ago when we were driving the orbital speed, but we're gonna do it again. G mass of the Earth, mass of satellite over the orbital radius squared, divided by mass of the satellite, because that's the object for which we're summing the forces. So let's cancel the mass of the satellite. Okay, and remember, when an object goes in a circle, the acceleration is v squared over r. So we'll do v squared over r equals G mass of the Earth over orbital radius squared. Okay, now if this object is going in a circle, what is its orbital speed? Speed is distance over time, right? And the time is the period to go one all the way around once. So knowing that, let's substitute this expression for speed in for v. So that'd be 4 pi squared r naught squared over orbital radius. Oh, forgot my period. Period squared equals G mass of the Earth over orbital radius squared. One of these r's will cancel. Let's get rid of this one and one of those. And if we rearrange it, we'll get t squared over r naught cubed equals 4 pi squared over G mass of whatever is being orbited. So I'll leave the subscript off, but because sometimes it's not the Earth that's being orbited, it might be the sun, it could be anything. So that should be a square, not a subscript. That's better. Okay, so that's Kepler's third law. I think you should write that down because we're going to use it in a minute. Okay, how did we come to that? We derived it. we started from first principles, and then we took other relationships we were familiar with, we substituted them in, we did a series of mathematical steps, and we simplified. But remember, we started with a force diagram. That's the real secret to success. Okay. So this is the hardest part of today, which is getting the potential energy. No, we're trying to get an expression. We're trying to derive an expression for the potential energy, gravitational potential energy between any two objects. So if you remember, change in potential energy is the negative of the internal work done by a force. So let's write that down. Delta U, which is U final minus U initial, is equal to the negative integral of the force from R initial to R final, negative G, let me write it out more generally first. F of R dr. Okay, I'm hoping that equation looks familiar to you from the past, and now we're going to apply it specifically to this situation. So what is our force? If you're talking about an orbiting object, that's the gravitational force, right? And it's negative because it's attractive. Now those two negatives will cancel. So I'm going to make them disappear. And I'm going to pull out the GMM because those are constants. So GMM integral from R initial to R final of 1 over R squared dr. That's what we're integrating. Okay. So if we integrate 1 over R squared, you get negative 1 over R, right? So I'm going to do GMM negative 1 over R from R initial to R final. And if you simplify that, it would be negative GMM over R final plus GMM over R initial. Okay, so that is the change in potential energy. Now, whenever you had, let's say, a ball rolling down a hill or a roller coaster, where did you guys put potential energy equal to 0? Sometimes you put it at the bottom of the roller coaster. Sometimes you put it at the top of the roller coaster. I hope you did enough practice with that to realize that it doesn't matter where you put potential energy equal to 0, because you're normally interested in the work being done, which is based on the change in gravitational potential energy, which for the roller coaster or the ball rolling down the hill was the difference in height, right? Okay, same story here. It doesn't matter where you put potential energy equal to 0, but I think the easiest way to do it is to choose the potential energy equal to 0 when the force is 0. So we're going to say U initial is 0 at, well, U initial is 0 at R initial equals infinity. Okay, so our arbitrary choice for having potential energy 0 is at R equals infinity, which means now we can write our expression at any point. The potential energy, the gravitational potential energy, is negative GMM over R. Okay, there's a few things to notice about this expression. First of all, there's two objects, right? So in order to have potential energy, you need at least two objects, because potential energy is a form of stored energy due to the location of the two objects. These two objects are interacting with each other. So that's thing one that we notice, is that you have to have two objects in order to have, at least to have potential energy. Another thing you might notice is the potential energy is negative. So it's negative because if you think about it, these two objects are bound to each other. You know, they're pulling each other together. So you would have to do positive work to separate these two objects. So if you look at if we graph this function of potential energy versus separation between the two objects, it would look like this, right? So that means that as the objects get infinitely far apart, their potential energy approaches 0. Okay, so if I were to separate two objects from, let's say, our initial to our final, the initial potential energy would be here, and the final potential energy would be here. So you would have to do positive work to get the two objects apart, to pull them apart, and you would be increasing its gravitational potential energy, because you can see it becomes less negative the farther they get apart. Okay, so let's just say it one more time. So for gravitational potential energy, you need to have at least two objects to have potential energy. It doesn't make any sense if you have a ball rolling down a hill, the ball itself can't have potential energy alone. The reason the ball has potential energy is because it's in the Earth's gravitational field. So it's much more appropriate to say the ball Earth system has potential energy. Okay. Yes, so the energy is stored in a system of at least two objects that are interacting with each other. We chose arbitrarily that the potential energy is zero when the force is zero. And an external agent would have to do positive work. And if you do positive work, work is a transfer of energy into or out of a system. So if you do positive work on a system, you're giving it energy. And where did that energy go? It increased the gravitational potential energy. It became less negative. Oh, okay. So this one's really easy. Kinetic energy is a million times easier than potential energy to understand and also to derive. Okay, so kinetic energy, you guys know, is 1/2 mv squared, right? If we want the kinetic energy of a satellite, we're going to plug in the mass of the satellite, and then we derived the orbital speed of any orbiting object a moment ago. It was the square root of gm over r. That's the orbital radius. And the capital M is the mass of the object that's being orbited. Okay, so if, oh, I forgot to square. Okay, if you square that, you get gmm over r, orbital radius, over 2. There you go. So this is the equation for the kinetic energy of an object that's in orbit. And I didn't put the subscripts on because we don't know what's going to be orbiting and we don't know what's going to be orbited. So the capital M is the object that's being orbited, could be the sun. The lowercase m is the satellite, could be a moon. And then R O is the orbital radius. Okay, much easier in comparison to potential energy. Total mechanical energy, I mean, we're pretty much almost there. So let's just finish the job. You know do you know that mechanical energy is the sum of kinetic and potential? So it's kinetic plus potential. And the kinetic energy we just derived, I think it was gmm over 2r. And then the hard work we did to derive the expression for potential energy was negative gmm over r. Okay, so what we need here is a common denominator. That's no problem. So gmm over 2r minus 2gmm over 2r gives us total mechanical energy is negative gmm over 2r. Okay? So that's your total energy. It's inversely proportional to the radius. I think you guys should write that down because we're going to use it in a minute. Okay. Adrastea is a moon of Jupiter. Calculate its orbital speed. I'm going to give you guys 1 minute to try that. Okay, so hopefully you wrote down the equation for orbital speed. If not, you could just derive it really quick using a force diagram in Newton's second law. So the orbital speed is g squared of gm over orbital radius. So let's plug in our constant. Plug in the mass of the object being orbited. Oh, so I purposely put in two masses here to see if you guys knew which one to use. Should we use the mass of the satellite or the mass of the object that's being orbited? If you go back to our derivation, you'll see that this m stands for the mass of the object that's being orbited. So I hope you plugged in the mass of Jupiter divided by the orbital radius. Here's another place where you could have gone wrong. Did you guys convert to meters? I put it in kilometers. So I hope you converted it. You should have gotten 31,468 meters per second. So with sig figs 31,000, I hope that's what you got. Okay, same moon. Calculate the mass of Jupiter using Kepler's third law. I'll give you 1 minute. Okay, so let's start with Kepler's third law. Okay, now in this case, the object being orbited is Jupiter, and we want to solve for the mass of Jupiter. So let's do that first. When it says calculate, you need to rearrange the expression so that you solve for your unknown first, and then you substitute the numbers. So let's do that. I don't know why I always write the subscript instead of the superscript. Okay. Okay, so the mass of Jupiter is 4 pi squared times the orbital radius cubed. Did you guys convert it into meters this time? If you messed it up on the last problem, hopefully you got it right this time. Divided by period is 0.3 days. 1 day is 24 hours. 1 hour is 3,600 seconds. Okay, if you plug all that in, you should get 1.94 times 10 to the 27th kilograms. Okay, so that's how you would use Kepler's third law. Okay, how much energy is needed to move an object from the surface of the Earth to an altitude of twice its radius? I'll give you 1 minute to try it. Okay, so when we say how much energy is needed to move an object from the surface of the Earth to an altitude of 2e, what you're interested in is how much does the potential energy change. So let's draw a picture. So you have the Earth, and then you have an object on its surface. So originally, the distance between their centers is RE. And then later on, you want to move it to an altitude of 2r. It's not to scale. So this distance is 2 times the radius of the Earth, not r3, radius of the Earth. Okay, so that means that the distance between their centers after you move it is 3 RE. That's half the battle, is just drawing a picture and figuring out what the distance between their centers are in both situations. So, okay, now that we have that, I think it's not so bad. So delta U is negative GMM times 1 over R final minus 1 over R initial. I factored out the GMMs. And R final is 3 Earth radii, and our initial is just 1 Earth radius. So what do we need? We need a common denominator. That'll be 3 RE. 1 minus 3 is a negative 2. And then the negative out front will cancel. So we're going to get delta U is positive. That means that the potential energy increased. So it would be 2 GMM over 3 RE. Then you got to plug all the numbers in. Okay. If you plug all that in, you should get 4.17 billion joules. It's a lot of energy. So the energy you need to move something, that's basically the work you need to do, is equal to you're going to need to do positive work because you're increasing the potential energy of the system. Okay, this is a tough one. I'm going to let you try it. Okay, I'm going to give you a minute and a half for this one. Okay, so we have to think about the system's kinetic energy and its potential gravitational potential energy. So we want to know the change in internal energy. Let's just take a picture. Draw a picture real quick. If you have an object in orbit and then it slows down, maybe there's a dissipative force acting on it, it's going to crash into the Earth. So it slowed down. So its kinetic energy decreased. Where did that energy go? It went into internal energy, maybe a transfer of thermal energy out of the system. Also, let's look at its potential energy. We got to go back to that graph again. Potential energy versus their separation. So they got closer, right? If they got closer, you're moving from maybe this point on the curve to this point on the curve. So what that means is the gravitational potential energy decreased. It got more negative. Where did that energy go? Well, it transferred into internal energy. It didn't just disappear. It has to be accounted for. It went to internal energy. So my strategy for doing this problem would be just to get the magnitude of the change of the kinetic energy and add it to the magnitude of the change of the gravitational potential energy, and then you'll get the change in internal energy. So let's just do absolute value of delta K, and then we don't have to worry about signs. If we accidentally do initial minus final or final minus initial, it won't matter, plus the magnitude of the change in potential energy. Okay, so let's get the initial kinetic energy first. Remember, we derived that expression for kinetic energy of an orbiting object, gmm over 2r. So you would get I didn't put the mass of the Earth down here, so I don't know how far you guys were able to, maybe you had it on your paper from earlier. It's 5.98 times 10 to the 24th. Okay, now the orbital radius, if you look at our picture, would be the radius of the Earth plus the altitude, which is another 500 kilometers. So the radius of the Earth is 6.37 times 10 to the 6 meters plus 500. You got to convert that to meters, right? So 10 to the 3 times 10 to the 3 meters. Okay. So the initial kinetic energy of this satellite is 1.45 times 10 to the 10th joules. Okay, now the final kinetic energy. We cannot use that equation we just used because as it's hitting the Earth, it's no longer in orbit. So we just use the plain old vanilla 1/2 mv squared. So we know that the mass of the satellite is 50 kilograms, and they gave us the speed is 2,000 meters per second. I hope you guys converted that. Let's get rid of this picture. Okay, so the final kinetic energy is 1 times 10 to the 9th joules. Okay, so let's find the change in kinetic energy. The change in kinetic energy would be 1.35 times 10 to the 10th joules. That's how much kinetic energy was lost. Where did it go? It went into internal energy. There was probably a transfer of thermal energy out of the system, out of the satellite Earth system. Okay, then we need to get the change in gravitational potential energy between its original position and its final position. So we've done this before, but it's negative GMM over R final plus GMM over R initial. And I guess we could pull out the GMM. Okay, so equals, here, I'll just do this. GMM times 1 over R initial minus 1 over R final. Hopefully you guys are okay with that algebra. I just flipped the order so that I didn't have a negative in front. Okay. Oof, I'm gonna run out of room. Okay. So that's what I took out. And then I'm gonna have 1 over our initial minus 1 over our final. So, okay. I think you're going to have to trust me on this one, guys. Well, I'm just going to tell you, hopefully you got this on your own, that the delta U, I got earlier 2.19 times 10 to the 9th joules. Okay, so our kinetic energy decreased by 1.35 times 10 to the 10th joules, and our potential energy decreased by 2.19 times 10 to the 9th joules. So if you add those two together, that's your change in internal energy. So I'm going to go back up here, and I'm going to add those two together, and you should get 1.57 times 10 to the 10th joules. Okay. I think I might have made a mistake somewhere. Oh, no, that's right. That's right. Okay. All right. So our answer is here. That was a tough one. Oh, my goodness. The main idea is that you understand that energy is conserved. If work is done, that means energy is being transferred into or out of a system. Okay. Okay. Why don't you guys try this one? We're going to switch off the sun's gravity. And if you do that, then we know from Newton's first law that an object in motion will continue in a straight line at constant speed unless there's a force to change its state of motion. And right now I'm going to get rid of that force. So Mercury and Pluto Mercury, you guys know Mercury is closer to the Earth right now. Would it ever be farther away if we turned off the sun's gravity? Okay, think about that. Try it. Okay, I hope you guys drew a picture because that's really the only way to figure this one out. If you have the sun, and then you have the just Mercury, and you have Pluto, I'm not drawing these to scale in any way, okay? So if you have, they're in their orbits, this is Mercury and Pluto. All right. If people are going to be picky, we'll call them satellites. How about that? Okay. Mercury is moving always tangent, right, to wherever it is in its orbit, and so is Pluto. Now, these velocity vectors, this is the speed of Mercury, and this is the speed of Pluto. Now, they're obviously not to scale. Nothing in this diagram is to scale. I'm just trying to get a general sketch of what's going on. And if the sun stopped pulling on these things, Mercury would continue in this way, Pluto would continue in this way. They would just stay in a straight line at constant speed. So I think what we need to do is figure out how fast these two planetary objects are moving. And then we can see who's going to win the race. All right. So orbital speed of Mercury is the square root of g mass of the sun divided by the orbital speed of Mercury. Remember, the mass, when we derived it, is the mass of the object that's being orbited. Okay, so let's plug that in. Okay, if you plug that in, you should get the orbital speed of Mercury is 47879 meters per second. So with sig figs, 47,900 meters per second. Now let's take a look at Pluto. That would be square root of g mass of the sun, because it's still orbiting the sun, divided by the orbital radius of Pluto. 6.67. Divided by the orbital radius of Pluto. And if you plug that in, you should get 4739 meters per second. So which one is moving faster? Mercury is moving faster, 10 times faster, right? So that means that if Mercury is moving faster, eventually it's going to overtake Pluto and it'll be further away from the sun. So the answer to this question is yes. Okay, so I want you to find the mass of the Earth using Kepler's third law. Okay, so we're going to use Kepler's. Oh gosh, I keep doing this, the subscript instead of the superscript. 4 pi squared. Okay, so we're trying to find the mass of the Earth. So let's solve for that first. Would be 4 pi squared r cubed over gt squared. Okay, so for the mass of the Earth, you get 4 pi squared times r, 3.84 times 10 to the 8th meters. We're using that as the orbital radius. Talk about that later. And then the period is 27.32 days. And I didn't cube that. If you solve for that, you're going to get 6.02 times 10 to the 24th kilogram. But that's not the number that we've been plugging in every time we use the mass of the Earth. So what gives? Why did we get a bigger number than we should? Let's look at our equation up here for the mass of the Earth. So the mass of the Earth is proportional to the orbital radius that we use cubed. And the orbital radius we used was the distance between their centers. But if you look at the Earth and the Moon, they don't orbit about the center. They orbit about their centers of mass, which is a little bit closer to the moon. So we used an overestimate of the orbital radius, so we got an overestimate of the mass of the Earth. Okay. Okay, I'm going to do this one with you because we're running out of time. You have an object that's released from rest at an altitude h above the Earth's surface. Okay, so here's the Earth. You're releasing it from a distance h above the Earth's surface. And then later on, it's going to be a distance r from the center of the Earth. Okay, so initially it didn't have any kinetic, but it had potential energy, and the distance from the center would be radius of the Earth plus h, right? Because this is the radius of the Earth. And then afterward, it's going to be moving. When it impacts the Earth, it'll be moving. And the distance between their centers they gave us is lowercase r. So let's cancel the mass of the object that we're dropping. And if you solve that for v, you should get the square root of 2gm times 1 over r minus 1 over radius of the Earth plus h. I took the second term on the right and I added it to the other side, and then I multiplied by 2 and took the square root. I did a lot of algebra in one step, sorry. Just because we're running out of time. Okay, just to summarize what we did today. We used a force diagram and Newton's second law to derive the orbital speed of an object. It's inversely proportional to the square root of the distance between the centers, the orbital radius, let's say. It's really the orbital radius. Then we derived Kepler's third law using a force diagram and Newton's second law. We found out the relationship between the period of a object that's revolving around another to the orbital radius. And then we found the gravitational potential energy. That was the hard part. We found that it's negative. You would have to do positive work to separate the two objects, and its potential energy would increase because it's becoming less negative. We found out you need two objects to have potential energy. And yeah. And then the total mechanical energy of the satellite Earth system, that was just a simple algebraic derivation we did. After the really tough potential energy, we added it to the kinetic energy to get this. So it's inversely proportional to the orbital radius, and it's negative because it's a bound system. I'm going to leave you with this for homework. If you could try it tonight, that would be great. This is an old AP question, so if you can do this, that means you're kind of up to the level you need to be. And then tomorrow we are going to start review. So we're going to start one-dimensional kinematics tomorrow. I hope to see you tomorrow, and stay home and stay safe.